This is an intro video to Module 8, in which we're going to be looking in section 5.1 and looking specifically at the spring mass system of free undamped motion. And basically what we want to see here is that we can use some of the differential equations that we learned how to solve in chapter 4 for applications in modeling a number of mechanic problems, and in this case the spring mass system. So suppose we have a spring like this one, and we're going to say that L is the length of the spring before it gets elongated or it gets pulled down by any weight. And then S is what it, if I put a mass on it and it comes down to an equilibrium, to a place where it's not moving, then we say the spring would have moved down to L plus S. Okay, now the law that we're going to use to model our differential equation is to begin with is Hooke's law, and this one says that a spring will exert a force opposite to the direction of elongation. So the direction of elongation now is downwards, so a spring will exert a force upwards in our case here, and proportional to the amount of elongation. And so that gives us that the force is some K times S, where S is the amount of elongation and K is some constant of proportionality. Now, if we pull on the mass downward by an amount, say X, then we're going to make this spring and this mass move up and down, right? And so we're going to assume that the spring and the mass was at equilibrium at a point S. Then we know that at that point the force moving that's going upwards, which is Ks, has to be equal to the force that's pulling downwards, which is mg. And then we displace it, we pull it down by just a little bit, and it starts vibrating, going up and down. Then we're going to use Newton's second law and say that, well, force is m times a, where a is the acceleration. And in our case, the force that is acting is the force that is acting upwards, which is K times the amount of elongation, in this case is S plus X. And then and we're going to say that that upwards side is we're going to describe with a minus sign, and then there's a force pulling down, which is mg on the mass. And so we can rewrite that and combine like terms and so on, and get that ma equals minus kx. So again, as we pull it down, that's what would happen to the spring, and we come out with this dE of free undamped motion, which is the second derivative of x with respect to t, and that's a plus k over m, where we've divided by m and moved kx to the left hand side, times x equals 0. Well, notice that this is a second order linear homogeneous differential equation with a constant coefficient. So section 4.3 we learned how to solve these types of differential equations. Now, starting with this equation, something that is traditionally done is that we substitute this k over m with an omega squared, and then we come up with this differential equation where omega squared is understood to be k over m. We can find the solution that tells us where the mass is in time as time changes. Again, by the methods of section 4.3 is how we find that solution. And then there's a couple of things that we'll be interested in. We'll be interested in understanding the period, or the time that it takes in seconds for the mass to execute one cycle of motion. Meaning if you're at the very top highest point, then it goes down, all the way down and back up to that highest point. That would be one cycle. And also we'll be interested in understanding the frequency, or the number of cycles per second. And you'll use that in some of the problems. So this is one example in which we use those differential equations. There's many more in this chapter that you might be interested in looking through at how these differential equations we learned how to solve do appear in examples that we model in everyday science, and in this case mechanics.